You take your time, no hurry. So I recording this particular video, and the first part is just the homework problem. Homework, the class we need to work through number 7. So this is number 7 homework problem. It says prove equation 1.4.15, and that was the equation down here. And then second, if we place the photo detector along the P port or B port, find the probability density rho sub B. In the textbook has a printed wrong. Put the capital letter P. Actually, this is a rho sub B and the delta like this. So many did very good job here. The only small thing that I noticed was that when you guys to write this down, just be careful. Whenever you write on this, for instance, if you want RT, you should not use capital letter R or capital letter T here. Only at the very end, you can do that. In other words, what I saw some of you wrote like this. Capital letter R, square root capital letter R. Of course, you would think that's just a small r like this. And because that's us. But the problem was in quantum mechanics, we have a face. That's a problem. If we have a face, if you take square root versus not square root, so that's become non-trivial. So just be sure, do not try to use a square root R. Instead, if you have two R's, you have R star like this. The trouble was that in the end, if you have this term, you're lucky, like this. So this gave you capital R, which is perfect. But what happens if at the end you will get R, watch carefully, T star. If you have this, then you're going to stuck because you cannot take square root R, but there's a phase factor. So this was the issue. So this was the issue that I want you to know that. In other words, just be sure do not replace this lowercase r, capital lowercase t with that. And then you solve for that. And the next term, so you solve for this. All you need to do is start with this equation and then compute a complex conjugate of whatever you had, and then you have this expression d over 2r. Now, only at this step, you see, I have r squared, and this will be equals capital R. T squared is going to equal capital letter T. And only at this location, yes, you can write them down. So even though the final answer probably is similar, but the sort of physical thinking is quite different. So this is one that I want you to know. And I really like Cody's work for the part B. Part B, Cody did a really wonderful job and working all these details. But one thing that small things that you probably didn't realize was the following. Now we work out of mathematics. So essentially what we do, if we put a detector around the B direction, so you're going to have a B direct brackets and S. So this is what you will get. And then do the complex conjugation, you get this expression. Now this expression is very interesting, which means if you this row sub A, add a row sub B, add them together, you're gonna these two terms cancels out. You see, the second terms cancels out. You're gonna have T squared plus R squared and plus 2RT. Now, when you do that, you will end up with next equation, which is over here. So I'm going to show you here in my answer. You see here, and you will end up with this expression. Now, this is T plus R per n square, and you will get this one. And Cody thought, oh, T squared plus R squared equals 1. No. T plus R equals 1. So it's not a T squared plus R squared. It's a T plus R. When I look at the answer, it looks beautiful. And then I thought myself, whoa, there's something going on. And then I realized it was a T plus R equals 1, not T squared. And then you can see if both detect, you get 100%. There's no question about it. This is the only one that I think you need help. The other ones I already posted here, and let me go back see whether I have another one here. Yes, I do. Okay, let me just go back here. So another assignment, which is the I think let me look at this one. If I see some errors, I will notify you. So, okay, so this almost everybody get it correct. In other words, the final expression. And so this one. And one last one is the proof of the wave function, which is this proof here.
Was
Then,
using harmonic because you said use the general methods, because you said give an example, and I used that harmonic oscillator.
yes, you could do that. You could do that. But the problem was that this question was asking for the generic solution. You can use a harmonic oscillator. That's perfect, no problem with that. And the only thing that this problem asks for a generic solution. So that's the difference. So here, what I showed you here is a generic solution, which is a second problem. So what I do, you see, I just use the time-dependent Schrodinger equation. And you may wonder, Dr. Zhang, why don't you use the time-independent Schrodinger equation, which you could do too. There's no problem. The only thing that you need to be careful was the time-independent Schrodinger equation is eigenfunction. It's eigenequation. So now it's not generic, but time-dependent Schrodinger equation is generic. You can use any functions, anything, just plug it in. Just plug it in. Because that equation must be correct. But the time-independent Schrodinger equation is very restricted. Only allowed to have something in order to get the correct answer for the eigenstate. So that's the one. And then you can see I plug it in and then just minus each other. So you will get this equation here. And this equation, your phi cannot be zero because that's what function. If phi zero doesn't make any sense on both sides, it will be zero. So V1 must be equals V2. On the other hand, if you have two wave functions, psi1, psi2, and they both are good wave functions, you can have one potential, have two wave functions. This is actually called a degeneracy, which we will discuss in next, well, not next chapter, chapter after next chapter. And we will talk about degeneracy, which means one energy, you have two states corresponding. In this case, it is a case. You see, I still starting from time-dependent Schrodinger equation minus each other, I get expression. You see, oh, I missed, I should have put an equal sign here, forgive me. Yeah, I need to put an equal sign. And so this equal to each other. So you see, psi is still, the psi 3 still, it's a good wave function. So that's one. So you can prove this rigorously. Any question on this? Any question? No question? Good. Okay. So I'm going to stop sharing and I'm going to end this the presentation. Now I'm going to start with the question for you guys for the last class. All right. So here is what I'm going to do. Let me share the screen here again. And I'm going to share this. So let's see whether you still remember something. Okay. All right, first question. Why do we use the wave function superposition principles to find a time-dependent wave function? Okay, so why we do that, Cody? Why we use the wave function superposition principle to find time-dependent wave function? Yeah, look at the notes. Look at the notes. So why we use the superposition principle? This is a very important principle. Why we do that? Okay, Aisha, can you help? Yes, it's keep on going. Mixed of what states? Mixed consists of what? You remember C1 phi 1 plus C2 phi 2, right? What is a phi 1 phi 2? What these are? What kind of states they are? Pure state, and this is also called. No. This is also called this pure state. And why we call it pure state? Because they are also a word start with E. Second letter is I. Exactly, because they are eigenstates. They are eigenstates. Could you guys write this down? Write this down in notes. The main reason why we use the wave function superposition principle is because these superimposed ones, like phi 1, phi 2, phi 3, whatever, they are eigenstates. They're eigenstates of the system. The eigenstate system, if they're not eigenstate, we probably won't be interested to expand it. We could, but we might not be interested at all. So that's a real important because they are eigenstate. Now you may wonder why the eigenstate matters. So here is the reason. Because we know eigenstate wave function, the time-dependent wave function for the eigenstate. Because we know it, because we know the time dependent wave function for an eigenstate. Okay, then the question is what it looks like. What is it? In other words, what it looks like for the time dependent wave function for an eigenstate. Okay, and this is a very important concept. In other words, could you guys look at the notes? You know, what happens if I have an eigenstate? What the next moment t not equals 0? What the wave function is going to look like? What wave function is going to look like? So t equals 0, you have phi 1, 0. What about phi 1 of t? What that is? Did you find it somewhere? Not really, just before that.
The linear.
Yeah, linear combination. And we have solved, you remember we separate the spatial part with the time dependent part, remember? And we have a function called f, right? You remember we have function f. What the f function looks like? What the function f look like? We have separate variables, separate the spatial part from the time dependent part. Separate them. Once we separate them, we have the exponent. You guys remember exponent? Okay, let me show you. Exactly. Look at my screen. That's it. Did you get it? In other words, the time-dependent portion is just this factor multiplied by whatever your original t equals 0. Could you guys write this down? This is the most important factor. In other words, if I have eigenstand phi n sub n, then the time-dependent ones is going to be this factor times phi n, so that t equals 0. So then when you expand this, the whole thing just becomes much simpler. All right, next, what are the three main properties of wave functions? Three properties of main wave functions. Could you look at that? We talk about two at least.
Yeah, isn't it the temporal, like time and space one?
No, that's the separation of variables. And you remember the wave function has to be, what wave function has to be if the mutually must be, one must be, if I have a wave function, give that to you. What we did first time on board, what we did first thing on the board, do you remember? A word started with the N. Exactly. The first thing, the property is normalization. Could you guys write this down? Normalization. Second is orthogonalization. You must be perpendicular to each other. Okay, so these are three things which you need to remember. So these are the one that I was talking about. And this is the one that I think, okay, very good. Let me see, I can get progress to next. All right. So these are the three main properties and the wave function. So today we are going to go started with from here. Do I have another one? Okay, that's it probably. All right. So we're going to use a board now. We do not need Zoom anymore. So we're going to stop sharing. So, and today we're going to continue on the, let me stop that and stop recording. So we're going to